Today I'll be presenting the groundbreaking new study creatively titled What's Up with the Speed of Light, Blackbody Emitters, and Line Spectra. First, I'll start by giving a brief introduction of the research goals and hypotheses. Then I'll give an overview of the theory and methods used in this experiment. I'll then present the data obtained and give a conclusion. The first goal for this experiment was to better understand some basic phenomenon associated with light energy. This was done by calculating the speed of light. It was also explored how different blackbody emitters varied with temperature. Another goal was to provide evidence for the quantized nature of electronic energy levels. This was done by looking at the line spectra for hydrogen and deuterium. The Rydberg constant for these two atoms were also calculated using this line spectra and compared. So the reason that this experiment is so incredibly important is because for the first time, the speed of light was able to be accurately calculated. The speed of light is a fundamental constant of nature. It also allows for the equivalence between mass and energy to be seen. Blackbodies were also studied in this experiment. A blackbody is an idealized body that radiates at all frequencies with a spectral energy distribution dependent on its absolute temperature. As seen in Figure 1, it was originally predicted by scientists that as wavelength increased, energy would continue to increase, even in the ultraviolet region. But this led to the ultraviolet catastrophe because in the ultraviolet region, even though the wavelength is increasing, the energy decreases. This leads to the theory that energy must be quantized. And this explains this phenomenon because modes with a higher frequency are less likely to become excited. So the average energy of these modes decreases, which is why we're seeing a decrease in the ultraviolet region of the spectra. The atoms act like blackbody emitters because they also absorb and emit radiation. So the quantized theory can also be used for atoms. The line spectra of hydrogen and deuterium was also measured in this experiment. Because of the quantized theory, molecules can only exist in certain discrete energy states. And because each atom has a unique spectra similar to a fingerprint, spectroscopy can be used to characterize molecular compounds. So the first hypothesis goes along with the speed of light. And it states that the speed of light should be most accurate when measured at a greater distance because the returning beam and the outgoing beam should have the most similar distance measurement. The second hypothesis goes along with the blackbody portion of this experiment. And it states that the sun follows Planck's blackbody function the closest out of the blackbody emitters studied, since its temperature is the hottest, meaning more light is given off at all wavelengths. And the final hypothesis is in regard to the line spectra. And it states that the ionization energy will be higher for deuterium since it has a larger atomic radii, meaning a smaller amount of energy is required to remove the electron from the outermost orbital. So this figure describes the experimental method used to determine the speed of light. So a laser was focused at a turning mirror, so it bounced back at a returning path detector. This allowed for the flight time of the beam to be measured, as well as the distance of the total path to be measured. So for the blackbody calculation, an ocean optic spectrometer was used to collect emission spectra for various blackbodies. And these emission spectra were fit to Planck's blackbody Planck's blackbody function, which is seen in yellow. For the line spectra portion of this experiment, a monochromator was used to disperse the light emitted by the hydrogen and deuterium discharge lamps. And then the following equation in yellow was used to determine the Rydberg constant for each of the atoms. So as seen in figure 3, there are different energy levels based on this quantized theory. So at a higher excited state, there's going to be a longer path, which means there's going to be more energy. And because the energy is higher, the wavelength will be shorter. So this slide shows the results for the speed of light experiment. So figure 4 shows the oscilloscope of the distance measurements of 60 feet. So in this first table, the speed of light was directly calculated by just dividing the total length of the beam by the flight time, and then the values were averaged. But a better calculation is actually doing a linear regression of distance traveled versus flight time, with the slope being the speed of light. So if you compare the error between these two methods with the linear regression model acting as the literature value, because it should be more accurate, these error values are obtained. So this fits with hypothesis 1, although not completely perfect, because the longest distance doesn't have the smallest error, but it does have a significantly smaller error than the first couple measurements, which have a shorter distance. This next graph shows the spectra obtained for the 6 different bulbs and the sun. And this top table shows the max wavelength and the Wien temperature and Planck temperature calculated. The Wien temperature was calculated based on the equation max wavelength times temperature divided by the proportionality constant B. And Planck's temperature was obtained using the solver function in Excel to fit Planck's blackbody function to the experimental data. So figure 7 shows the spectra of the sun and how closely Planck's function is fitted to the spectra. There is some variance because a blackbody is theoretical. It's not going to be perfect, but it does follow it much more closely than the bulbs, because the bulbs contain, going back to the previous slide, the bulbs contain much higher intensities in the higher region outside the visible light spectrum, where the sun spectra is primarily focused within the visible light spectrum. Okay, this next figure shows the line spectra obtained for hydrogen and deuterium. So there are 6 different peaks seen, and within each peak this is a zoomed in window of one of the peaks. There should be 2 peaks, one for deuterium and one for hydrogen. So although it appears as only 6 peaks, it's actually 2 peaks within each of these 6 peaks. So as predicted, as the transition becomes larger, the max wavelength becomes shorter and the energy increases. The Rydberg constant was calculated experimentally using the slope as seen in Figure 9, and it was also calculated using the Bohr equation. So the Rydberg constant was lower for hydrogen because hydrogen has a lower mass, and it was higher for deuterium because deuterium has a higher mass. The theoretical mass of the nucleus for deuterium was also calculated and compared to the experimental mass of the nucleus, and the percent error was 11.4, which is a pretty good approximation for this experiment. And this final table is just calculating the experimental ionization energy versus the Bohr ionization energy. And it can be seen that there is a very low percent error between these two values. So in conclusion, the speed of light is most accurate when measured at a greater distance d. Energy is quantized and follows Planck's function. A higher temperature equals a more ideal blackbody emitter. Spectrum lines become closer together when further from the nucleus, and a larger mass means a larger ionization energy and a larger Rydberg constant. Thank you.